All right, my presentation was on space-time and general relativity. My name is Marcus Hems. Let's get right into it. So before getting to general relativity, we first got to talk about special theory of relativity. This was written by Albert Einstein, published in 1905, and it was widely ridiculed at the time, not just because he was Jewish, but also because it challenged the theories of Isaac Newton, who at the time was considered like the Michael Jordan of the physics world. And it established that the speed of light is constant, or invariable is how he put it, which means like constant always. This is a bit of a change up to what people might have thought. So for instance, imagine if you're like on a train, right? And you're passing by a bird, and there's a guy standing also looking at the bird. So for the standing guy, that bird, it's all moving forward here, the train and the bird going in the same direction. For the man standing, that bird is probably flying like decently fast away from him. But you on that train, you're going to be passing by that bird, and for you, that bird is moving behind you. Whereas for that man, its velocity is going forward. For you, its velocity is going backward. That's because its velocity is relative. But as it pertains to light, not the case. So let's say you're on like a super train that's going 100 million meters per second velocity. So absurdly fast, about a third of the speed of light, which is about 300 million meters per second. So if you're on a super train and you see a guy shining like a flashlight, like a really, really powerful flashlight, forward, going in the same direction you're going, you would not perceive the light to be moving at 200 million meters per second, like you might think. You would always perceive it to be moving at 300 million meters per second, at the same speed as the man standing with the flashlight is perceiving the light. All right. So Albert Einstein also kind of changed our understanding of gravity. It was previously believed that gravity was a mysterious attraction force between massive objects. And even Isaac Newton kind of knew that that really didn't hold up, but he couldn't really find the answer in his lifetime. Einstein kind of equated gravity with acceleration. And apparently he came to this epiphany or something by looking at a window washer outside of his window, and he's like, what if he fell? And he just started thinking about that a lot. But he kind of realized that a man standing within a closed-windowed spaceship, like something of that sort, accelerating 9.8 meters per second squared, directly upwards, would not be able to distinguish any gravitational difference between that enclosed space accelerating upwards at 9.8 meters per second and the gravity of Earth's atmosphere. But what if that same man shined a flashlight within that enclosed spaceship space? Einstein theorized that there'd be a minute difference in height from the starting place of the light, like the flashlight, and the ending place on the wall. Very, very minute, considering the distances involved here, but it would exist. So to see if Einstein's theory that acceleration and gravity were one and the same, for that to hold up, the same would have to be true on Earth when we're just standing still like this right now. That light would have to bend as well. That light would have to bend. And as it turns out, it does. Light does bend very, very minutely due to Earth's gravity, due to all gravity. Yes, because light bends according to gravitational fields. Now, mass's effects on space-time. The more mass an object has, the heavier an impression it leaves on space-time. There's a useful little video, where a guy has like this big old almost trampoline-looking like object in the middle of his room. I'm sure you've seen it, Professor, so I'm not going to waste your time trying to watch it. But to explain it, the fabric of space is like a malleable, taut, elastic fabric. And that's where the fabric thing comes in. Thinking of it like actually as a fabric myself helps, even though that demonstration that I was talking about it's a 2D model, so it's not entirely correct, but it's a lot easier to visualize than like a 3D model. It kind of just like breaks the brain a little bit. You're just trying to mentally think about that. So when an object is placed on this fabric, its weight is felt, and it droops a little as the fabric bends around it. Now, Einstein discovered that this is how gravity actually works. It's not some mysterious attraction force. There's a literal like dip in space-time that things kind of fall into. This resolved actually several unsolved problems that Isaac Newton's models couldn't explain, like the orbit of Mercury around the sun. Its ellipse wasn't like set. Its ellipse would orbit almost like a flower petal. And even then, it wasn't totally concrete, but the theory was further proven by Sir Arthur Eddington in 1919. Yeah, 1919. So during a solar eclipse, he found that the position of stars seen near the sun appeared to be distorted from where all their predictions told the scientists where the stars actually were. Obviously, he had to do this during a solar eclipse because you can't see the stars around the sun because it's too bright. But yes, the appearance of those stars, it was distorted from where they actually were because light was being bent by the huge comparatively huge gravitational field of the sun. So that's why that happened. So why is it called space-time? Like the time bit there. I've only really described the space aspect of it. We kind of touched on it earlier with light. So it's been established by special relativity that light moves at a constant, invariable speed, regardless of perspective or frame of reference. Light passing through a bend in space-time, a gravitational field still maintains its speed of around 300 million meters per second. This is in spite of the fact that a bend in space-time will not allow the light to reach from point A to point B in a straight line like it wants to. It has to curve with space-time that's being curved by mass. But despite this curve, light still maintains its total forward speed. So how can that be possible? Because the equation for speed is speed equals distance divided by time, distance over time. If the distance increases, then that must mean that speed increases as well. But we know that's not true with light. It's invariable. So something has to give here. And as it turns out, that it's not the speed of light that changes when the distance increases. Rather, it is the time which slows down within a gravitational field. So basically, the time increases with the distance to keep the speed of light constant. So time is perceived, well, not while you're in a gravitational field. It's a little difficult to explain, but time passes slower, essentially, within heavy gravitational fields than it would outside of one. I think I further explain it a little bit further. So yeah, the implications. So it's a bit hard to wrap your head around, but it's been proven with experiments. For instance, clocks on Earth tick slightly slower than clocks on the ISS because Earth's gravitational field causes causes space-time to just slightly bend, and that causes the time to basically be slower on Earth than it is out in the ISS, the International Space Station, where gravity is much weaker. And this is actually a plot point of the movie Interstellar, if you've watched that, where astronauts, the reason why this happens, we're like, this little maneuver is going to cost us 5 years or whatever the quote is because the planet that they're on is located very close to a super dense black hole. So the gravitational field there is huge, it's massive. So like only a couple of hours passes for them, the astronauts on that planet. But over on Earth, where the gravity is a lot lighter, it's several years pass. That's like a really extreme example. But let it be known that we have technically discovered a way to time travel forward. So you want to talk about implications. My implication is that I'm going to use this effect to escape this dying, primitive civilization. I'm going to wait out until we inevitably destroy ourselves. Maybe I'll have some time to finish my coffee before the end.